Welcome back to the classroom. My name is Mr. Wong. In today's lesson recording, I'm going to look at vector addition by resolution. So as you can see, breaking the vector components into two perpendicular parts from the resultant, or using the two perpendicular components to find the resultant that way. So we're going to look at specifically just problems related to this specific dot point. So let's go to the examples and go from there. Okay, so we have some force vector diagrams that we need to try and resolve and solve for. So for the very first one, we are assuming all masses in the diagrams are in static equilibrium, so they're currently stationary at this point, and it says determine the value of the vectors. For question A, we want to find the force, this force here, dragging it along this way, and the tension force, which is this force on the line. Okay, so what we know is this mass is 10 kilograms and it's pointing down because we know that is the weight force. So that's 10 times 9.8, that's the acceleration due to gravity. So we have a downward force of 98 newtons. Okay. Now I can sort of picture it in a couple of ways. I could picture the downward force being applied to the ball coming down in this direction here. Or it could be the same point as this direction here. The reason why I can say it's down this direction as well is because we can think of the reason why there is tension on the string, pulling it, is because of this downward force by, gravity. So you could write it like this here, or you could write it this point here. Okay, so by that same assumption, we can actually say this horizontal force dragging the ball in the left direction, that is essentially the horizontal component of the tension force. So that bit there, or that bit there, depending on how you want to draw it out. Okay, so as you can see, this is 40 degrees. If this is a 90 degrees intersect, because assuming that gravity goes, directly perpendicular to the surface, this would be 50 degrees. Okay, so you could use, in this case, trigonometry, SOHCAHTOA, to work out T and F here. Okay, let's try and change the color as we start to try and calculate them out. So let's firstly look at F. We'll use this 40 degrees. Over here is the adjacent side. Over here is the opposite side. So F would be using the ratios of tan theta. Okay, so I know that in this case, so F, okay, is over 98 equals to tan 40 degrees. Okay, because it's the opposite side. So F is 98 times or multiplied by tan 40. So that means F is equal to 82 newtons of force. Or at the very least, when we round it off to two significant figures, if it's three significant figures, we'll just do three significant figures for all of these, 82.2 newtons. Okay, so that's how you do that bit. Next point is to try to find the tension force. Okay, so my tension force here, I'll again use a different color so we can differentiate. Use red. We have this value here, the adjacent side, and here we have the hypotenuse. Okay, so we can use cos theta to work this one out. So in this case, the tension force could be written as tension equals to 98 over cos 40. And then the tension force I get roughly to 3 significant figures is 128 newtons. Okay, I derive this formula by rearranging from cos theta, the adjacent side is on top and the hypotenuse is at the bottom. So that's just rearranged into this at the end here, if you can sort of imagine. So that's how you do the first one there. Let's move on to our second example. In this case, we have a downward force of 36 newtons, okay? And it is attached to 2 other, let's assume it's like strings, and that's what we have here. Now, what that means is this downward force is providing the tension force of these 2 strings pulling up. They're balancing each other out, which means that the vertical component of these strings, or of this particular orientation, the sum of the 2 should equal to 36. Now we have 2 strings, okay? So if we have 2 strings, if I just draw the triangle out again, let's say, for example, this is F1 here, okay? This Y component that I have here, this bit coming up, that'll be 36 divided by 2, because there are 2 strings that are using this vertical force, okay? Next question is, what's the angle? The angle would be 45 degrees, assuming that this is going straight down, so it cuts directly halfway between the 2 lines. Okay, so that's relatively straightforward. So here we have if we're assuming this is the right angle triangle, we have an adjacent side here, and we have the hypotenuse. So we can use this formula that we wrote up here as well. So F1 is equal to 98. In this case, that's the adjacent side that we have here. So this would be 36 over 2, which is the same thing as saying 18 newtons. So 18 over cos 45. And that would give us a value of approximately 25.5 newtons. That's for F1. Okay, now F2, right? It's the same arrow length here. It's the same amount of vertical force, 18 newtons. It's pulling up, and it's the same angle we produce. So in this case, we know because we have the same angle, okay, the same vertical force, then F1 and F2 would equal each other. And so F2 would also equal approximately 25.5 newtons in that particular orientation. Okay, so there is that. Okay, now we move to question, now next set of questions, C and D. Okay, it says determine the value of the vectors. In this case, we are trying to find the resultant vector. I'm pulling upwards at 120 newtons, and I'm pulling this up at 160 newtons. Now, a common thing that I see students do is they try and draw this diagonal line and find the hypotenuse that way. The issue with that is if I'm pulling something up like this, and I'm pulling this along this way, then obviously the resultant force should be to drag it diagonally in that direction. Okay, so I'll get rid of this and I'll redraw it. So as I was saying, the resultant force should be going in this direction here. So if that's the case, is it still the same vertical force? Yes, it's still the same vertical force. So what I can actually do is move this arrow. I can move it up to this side here, or this horizontal line, I can move it up into this position here as well. So it actually works both ways. So I can draw it up here. I'll use a different color. Or I can draw it in this way. So I have this angle theta here, or this angle theta here to work on. So that's pretty good stuff. So that's the net force. So all we need to use is Pythagoras. Okay, so using Pythagoras, might not have enough space, so I'll use this bit below. Our net force is the square root of 120 squared plus 160 squared. That gives us approximately, or looks like exactly, 200 newtons. Okay, now because we want to find a resultant force, and this is a vector in 2D, we should also try and find the angle that it produces. Okay, so let's use this angle up here, because if I use this angle as reference, I can use it to find the true bearing of our net resultant. I'll write it up here. So in this case, theta is, what do we have? We can use tan. Okay, so tan inverse, the opposite side up here would be the 160. So 160 divided by our adjacent side, the 120. Okay, put that into my calculator and see what I can get. About 35 degrees. Okay, so in that case, I could write as the answer, the net force is 200 newtons with a true bearing of 35 degrees. Okay, so it's cool. Okay, and now we move to question D. Now this one's a little bit more interesting. We have two forces. One is directly horizontal, one is at an angle. So we want to find the resultant force. Now before you try and find the resultant vector, you need to firstly work out what the force components are for this 80 newtons at 30 degrees. So this vector here, this red one, let's actually keep it red for simplicity's sake. So it has a vertical component pointing upwards. Okay, so this vertical component would be 80 sine 30, and that would give you a value of 40 newtons this way. And it also has a horizontal component. Okay, to find that one, it would be 80 cos theta, because we have the adjacent side here and the hypotenuse here, 30 here, and that would be approximately 69.3 newtons. Okay, so that's what we have. Now if we do the add up, so say for example, if I draw it out, this 40, there is no other vertical component, so we can just safely draw this as 40 up this way. Okay. Here, this is 69.3 going in the opposite direction of our 100 in this direction here. So let's call this the negative direction, and I'll call this the positive direction, and I'll add them together. So my 100 subtracted by my 69.3, I get positive 37, or positive, sorry, I'll say that again, 30.7. So I'll draw this line over here to represent the motion that we have. So 30.7, okay? Use a different color just to signal that this is my resultant vector, and that's the angle in which we'll find the bearing, okay? This is my force, net force right there. Okay, so let's find the net force again. The net force is the square root of 40 squared plus 30.7 squared. So it is 30.7 squared, and we get approximately 50.4 newtons, and that is our net force. Okay. Next thing we need to find is the angle. So again, we're using tan inverse. We have the opposite side, which is 30.7, and then we have the adjacent side, which is 40. Okay, so put it in my calculator. So it'd be 30.7 over 40, and I get an angle of approximately 37.5 degrees. So let's just round it off to 2 whole sig figs for the angle here, because I'm going to put it in bearing. So 38 degrees. So in this case, the net force is 50.4 newtons with a bearing of 0.38 degrees. And that's how you do question D. Okay, now let's look at question E here. We want to find the tension force. We already have a downward force, and we have a horizontal force going in this direction. Same idea, let's go back to what we talked about before. We could imagine that the tension force is kind of popping down here, and we can move the 40 and make our right angle triangle here. But you can also imagine that the reason why we have a tension force is partly because of this, it's balancing out this horizontal force here. So it has a vertical component that's pulling up here to balance this arrow here. Okay, and it also has a horizontal force pulling in this direction here to balance out this 60 here. Okay, so that's our tension force. Remember, these are all in static equilibrium. So for this to be in static equilibrium, this tension force needs to balance these here. So that's 60 here, that is 40 here, and I already know that this angle we make is 40 degrees. So I can use any of these sides to help me find the value. So let's use or actually, if we have this case, even easier, we can use Pythagoras, okay? Because we have made a right angle triangle. So our tension force is effectively 40 squared plus 60 squared, and that gives us approximately 72.1 newtons. That was a lot more straightforward than I thought. But yeah, that's how you do it. Okay. Question F, find the resultant force of these two arrows. Again, if you recall, this diagonal arrow will have a vertical component here and a horizontal component here. This angle that we have here, assuming that this is going directly up, which is what a vertical component should do, these two angles should add up to 90. So that means this has to be 60 degrees, because 60 plus 30 is 90, okay? Now, the vertical component pulling up in this direction would therefore be 100 cos 60, which means that we have an upward force of 50 newtons. We have an arrow dragging along in this way. This component would be 100 sine 60, which is equivalent to about 86.6 newtons. Okay, so we have an upwards force of 50, and we have a force dragging it to the right at 86.6, added on with our 100. So if I redraw the line that we have a force that is going up at 50, up like so, and we have a force dragging it at about 186.6 newtons, like that, and we have a net force that is dragging it this way. And obviously, as always, we have theta right here. So if I want to find the net force, it would be using Pythagoras again. 50 squared plus 186.6 squared. That gives me a number of approximately, in 3 sig figs, 193 newtons. Okay. And then what we can do is find the angle. So we have tan inverse again. As you can see, majority of these questions, we are pretty much using the same type of maths. I guess the important bit is, do you know how to resolve for the diagonal vectors and placing them together? So that, and we get an angle of about 75 degrees. So again, our net force is about 193 newtons with a bearing of 75 degrees, and that's how you do that one there. Okay, now we're going to the last two questions of this video recording. It says for G, find the value of F. Remember, this is in static equilibrium, so if I say this is this midpoint here, if I'm dragging it this way at 600 newtons, then F would have to be at 600 newtons, but in the opposite direction. So that one's relatively simple. This is effectively solving for vectors in one dimension. So that's pretty good. That's relatively quick. And the last one, we have 3 arrows to compare with. Again, let's start with this one, this red arrow here. It has a vertical and a horizontal component. So I have 80 sine 30, that's our angle, that's the opposite side there. So that's roughly 40 newtons. If we look at this side here, that would be 80 cos 30, and we get 69.2 newtons. Let's call this the negative side for now, because I'm going to need to add with this arrow here later on anyways. I'll call that bit positive. We have a vertical component for this blue diagonal line or blue vector, and it is 60 degrees. Again, same idea as the previous question, they should add up to 90. So this is 100 cos 60, and that is about 50 newtons. Over here, we have 100 sine 60, and that would be about 86.6 newtons. Okay, so here it gets a little bit more complicated because we have multiple lines we need to work with. The net force is to go upwards. Okay, it's to go up like this. We have 40 newtons contributed by the red line and 50 by the blue line. So we have a net force of going up by 90. And if we have a look in terms of, in terms of what motion we have horizontally, we have negative 69.2, positive 86.6, and positive 50. So the net resultant force horizontally is to go in this direction at 67.4 newtons. Draw my vector arrow, goes this way, and I get sine theta here. So our net force is the square root of 90 plus 67.4 square. That is approximately 112 newtons. And then theta, in this case, would be that over that. And so we get an angle of 36.8 degrees. And that would mean our net force is about 112 newtons with a bearing of approximately 0.3 7 degrees. And that's how you do those questions. And that concludes this video that we have here. All right, so quick summary. Thank you so much for joining. What we've actually done is we've resolved the vector into a resultant vector into 2 perpendicular components. To do that, we had to obviously use these formulas here using trigonometry. We also tried to use 2 perpendicular vector components to find the resultant. In that case, we need to use Pythagoras theorem, and obviously to find the angle, we used tan theta in that related example. If you found this video useful, give it a like and subscribe, and I will see you next time. Thank you for listening.